So we're getting into trigonometry, and with trigonometry, we're studying angles. And angles, you can think of an angle as a measure of rotation. So we could have something say like this, and you typically see angles expressed like this. And you'll see another arrow that indicates that this here, we call these, oftentimes we'll call these legs. This leg was actually resting on this one, and then it rotated upwards. And you'll see angles of different types. This would be what's called an acute angle. And this is what's called a right angle. Pardon me just a second. Get a pen here. This would be, you might have seen this, and they tend to put a special symbol in here. But this is perfectly vertical. That leg's perfectly vertical. And you'll see this called a right angle. And we're going to talk about this. This is what's called a 90-degree angle. When that rotated leg is perfectly vertical, we call that a right angle. And then you might see something like this. This is obtuse. In an obtuse angle, it's bigger than a right angle. There's more rotation in it, but it doesn't quite reach the bottom here and become flat, which is another kind. This is a flat angle. And this is when you rotate all the way till you're facing the other direction. This is what's called a 180-degree angle. And again, we're going to talk about what degrees are. Finally, and this one can be a little tricky to draw because you got the two legs right next to each other. But one is going all the way around. And this is what we call, say, one full rotation. So these are very sort of qualitative ways of describing angles. Not a lot of rotations, acute. Perfectly vertical second leg is a right angle. Okay, it's not all the way flat, but it's more rotation than the right angle. We call that obtuse. When it does rotate, so it's flat, 180 degrees or a flat angle, then we can go all the way around back to where we started. And that's your full rotation. Now, the thing we want to do is we want to attach numbers to this. We don't just want to deal with descriptions. We want to actually attach numbers. And there's two ways we do this. Actually, there's three, technically. So how do we measure this precisely? Well, the precise method, one of them, is with degrees. And what we do, a degree is a small slice, if you will, of a circle. So this little slice, and this isn't drawn the scale. You'll see how this works out. But this could be, say, 1 degree. It's just going to be this one slice of a circle. Now, there's a requirement for degrees. There are 360 degrees in a circle, or 1 full rotation. I have to abbreviate rotation. So there should be 360 of these little slices inside this circle. So, for example, what is the measure of the angle and let's say we have something like this. And we've got our circle here, part of our circle. We've divided this up into little slices where each slice is a degree. I'll admit the accuracy of this, say if you put it on a protractor, is going to be a little bit off. But let's say in this example, each slice is 1 degree. Well, all we need to do is count the number of slices that fit inside this angle. There's 1, 2, 3, 4, 5, 6. So 6 slices equals 6 degrees. So that's how degrees work. Any questions about that? Now, there's something else we do with degrees, which is sort of unusual, but you might have heard of this before. We mentioned a little bit earlier. If I'm going too fast, let me know if you're still writing something. But you can have fractional degrees, like if you have 6.5 slices in here, you'll have 6.5 degrees. But there's another way of representing parts of a degree. And I should make this note right now just to save on writing. We would write 6 degrees like it's a temperature. So that can be a little confusing. The difference is we don't have degrees Fahrenheit, degrees Celsius. There's no F or C that comes after this. So we can represent degrees with that little circle there. Now there's fractions of a degree. And what we do is this. 1 degree is equal to 60 minutes. So instead of having decimal parts, we're going to talk about minutes. And then it breaks down even further. 1 minute is 60 seconds. So you'll run into this from time to time. You might see measurements in terms of minutes and seconds. Now, something to mention is 1 minute, we have a special way of representing that. Instead of writing the word minute, put an apostrophe. 1 second, put 2 apostrophes. So minutes and seconds have their own symbols. So let's take a look at an example. Let's say we have this. Convert 36.25 degrees into degrees and minutes. So the way we do this, we're going to take our 36.25. We're going to break it up as 36 degrees plus 0.25 degrees. And then we're going to do our conversions. We're going to use those same techniques we had from chapter 5. So this time, we'll multiply by a conversion factor. Well, that's what we did before. Now we have degrees on top. We want to convert this to minutes because it's a fraction of a degree. So degrees are on top. We need degrees on the bottom. So 1 degree is equal to 60 minutes. We do our multiplication. 0.25 times 60 is going to come out to 15 minutes. And then the way we write the answer, 36 degrees, 15 minutes. Questions about that? All right. Now, you can go the other way. And let me grab my calculator here. Let's say we have this. convert 2 degrees, 30 minutes, 45 seconds to degrees. So what we can do here is this. Well, again, we're going to write it as a sum. Now, this is already in degrees, so we don't have to change anything, but we do need to convert this, and we do need to convert that. So this will become 30 minutes. We want to convert minutes to degrees. So that means the degree will go on top because minutes is on top, and we need minutes on the bottom. And then for 45 seconds. Now, what's going to happen here? We're not going to convert this directly to degrees. We're going to convert it to minutes. So you have 45 seconds times 1 minute over 60 seconds. This will be 2 degrees plus, if you multiply 30 times 1 over 60, you come out to 0.05 degrees. And then this one, 45 times 1 over 60, it's going to be 0.75, but we want to be careful. Seconds cancel out, but we're going to be left with minutes. We still have minutes. So this will be 2 degrees plus 0.5 degrees plus, and now we need to convert minutes to degrees. This will be 2 degrees plus 0.5 degrees plus, and then let's see here. If you take 0.75 times 1 over 60, we have 0.0125 degrees. And if we add these up, 2.5125 degrees. And that's going to be our answer. Any questions about that? All right. So this is degrees. We talked about degrees as these little wedges, little slices of a circle that we can tuck into we can tuck it into an angle, and the number of wedges we can tuck in there, that's the measure of that angle. But there's another way of doing this. It's called radians. In the talk about radians, we need to talk about something called arc length. So let's say we have a circle. Now this is the center. And then on either side, the distance from the center to the edge of the circle, well, we've seen this before. This is called a radius. Now, the angle on the inside, we generally label angles. So the amount of rotation, I'm going to call this A, as a measure of the rotation. So we have that's our angle. Ooh, sorry, pins start to go a little bit. There we go. So that's our angle A. It's a measure of the rotation. It could be 30 degrees. It could be, say, something like that. And then this piece here is called the arc length. And this arc length it's associated or it's related to the size of the angle. If the angle is bigger, the arc length is going to get bigger. If the angle is smaller, the arc length is going to get smaller. Now, another way of measuring an angle is this thing called radians. And an angle measured in radians is this. It's the number of times the radius divides into the arc length. So that's what it means for something to be measured in radians. Questions about that? I'm sorry, I'm not sure you can see that. But it's the number of times the radius divides into the arc length. So what that's going to mean is something like this. Let's say we have a different angle. So here's our angle. measure of rotation, yeah, representing rotation. We've got the center of our circle, and let's say R is the radius. I'm going to abbreviate radius. Ooh, a little better job there. Well, let's say we take this radius and we try to place it alongside the arc length. So one radius would stretch here, and then we'd find we need a second radius to go meet it on the other side. So this would be a radius length. And this is also going to be a radius length. So we take this radius and we stretch it out along this arc length. What we're going to say is this angle A measures 2 radians. Questions about that? So that's the idea of radians, and now we have that to work with on with degrees. Now, a key thing to mention: many formulas in trigonometry assume, and this might be kind of surprising, but they assume angles are measured in radians. Even though you hear about degrees all the time, it's more common to measure things, at least when you do the computations with trigonometric formulas. We're going to look at some, but a lot of this is done in radians. So if degrees are so popular, because you're going to measure using protractors, those are in degrees. Well, how do you convert to this radians? What do you do if you measure things using degrees like with protractors, but then the formulas for trigonometry are using radians? What are you supposed to do? Well, good news is we can convert between the two. So 180 degrees equals pi radians. That's a common abbreviation for radians. And we'll talk about pi in just a second. So what that means is this. Now pi, this is a number that's approximately 3.14159, and it keeps going, actually. This is an irrational number. If you remember from when square roots, we took the square root of 2, and if you took the square root of 2, just get all these digits that go on and on forever. That's pi. It does that, and it's a very very useful number, and we represent it with this Greek letter here. And again, you've seen this before when we were talking about working with different area formulas. Oh, actually, you haven't seen this one. This is actually going to be new. I apologize. I'm confusing this with the survey of math class. We went through some of this. So this is what pi is. If you want to know where pi comes from, pi is equal to the circumference of a circle divided by its diameter. If you take any circle, now we got to talk about what a circumference is. The circumference, it's the arc length of an entire circle. So that's going to be circumference. We'll abbreviate circumference. But if you measure all around the outside of a circle, that's circumference. And the diameter is the width of a circle. You got to calculate this width. You got to make sure it passes through the center of the circle. That's the diameter. Abbreviate diameter. So if you have a circle, you measure carefully the circumference all the way around the circle. Then you measure carefully the width of the circle, making sure you pass through the center. There's going to be a perfectly straight line. Divide those two numbers, you're going to get something similar to pi. There's going to be little variations in measurement, so it might not be quite this, but if it's perfect, you're going to get that number. All right, so let's do some conversions. Let's see here. So let's say we have this. Convert 60 degrees to radians. Because again, let's say you're measuring something, you're going to use some trigonometric formula, but gosh darn it, they want the angle in radians instead of the 60 degrees that you worked really hard to measure. Well, we'll just convert it. We have 60 degrees times, we want degrees to cancel, so you have 180 degrees on the bottom, pi radians on top. Degrees top, degrees bottom, that means degrees are going to cancel. So we have 60 times pi radians. And of course, there's that little invisible one here. That's always going to be there. Our invisible one times 180. And the degrees are going to cancel. We're going to lose those. So you have 60 pi. Now, pi, it's like square root 2. So when you have an irrational number represented with a symbol, placing it next to a number, again, this is that algebra thing where we take that shortcut, means multiplication. Radians. Now on a calculator, there's usually a symbol for pi. If you don't have one, I would recommend using 3.14159. Let's see here. And so this comes out approximately around this. .047 radians or 1/47,000th of a radian. Questions about that? Now, another way you'll see this written you'll oftentimes see this written where they don't compute this as a decimal. Instead, they're going to treat it as a fraction and they're going to reduce it. And it turns out that 60 divides into 180. So 60 will go into 180 3 times. Now 60, we'll leave pi kind of off to the side. The 60 divides into 60 one time. So now we have 1 times pi over 3. And then we can write this, because 1 times pi will be pi over 3. You'll see this sometimes, but you might see this also, the decimal approximation. Questions about that? All right. So you might have to go the other way. Let's say we're going to convert 0.10 radians. Now, when you see a 0 like this probably suggests this was a measurement. So we're looking at 2 significant digits here. And with these conversions, when you're using conversions like this, they're considered to have infinitely many significant digits. The measured numbers, this one has 2, but something like this, we assume that this has infinite. So now we're going to do 180 degrees over pi radians. Because we want radians to cancel, we want degrees to remain. We've got our little invisible one here. And so that's going to give us 18 degrees over pi. And this one will approximate it. Approximately 5.729577951 degrees. Yikes. But this is going to be, we're going to assume this is a measure number. So we need to round this to 2 significant digits. So this will be approximately 5.7 degrees. Questions about that? All right. So we're looking at 10.1 here. The last thing to talk about in 10.1, and this will segue into 10.2, and that'll be it for today. But we're going to be looking at right triangles. So for this last part of 10.1, for 10.2 and 10.3, we're going to be looking at right triangles, and then we'll finish the course looking at non-right triangles. But this contains a 90-degree angle, or what's called a right angle. So it looks something like this. Or they might look something like this. Or something like this. But they have this perfectly vertical side. Now, sometimes they tip them over. You might see something like, they might play around with them a little bit and they'll tip it over, so to speak. They might do something like that. Might take this one and knock it over and get something like that. But they all contain this little symbol that says we have a 90-degree angle in here. Now, we're going to look at 4 properties. Well, really, one's universal and the others are very specific. But the first thing we're going to look at the Pythagorean theorem. And what the Pythagorean theorem says is this. This is one of the most famous formulas in trigonometry. So you have a right triangle. We have an A, we have a B, and we have a special side C. Now this side C is called a hypotenuse. And the way you know you have an hypotenuse, it's the side opposite directly across from the 90-degree angle. That's the hypotenuse. So the Pythagorean theorem says this. If you square and add the 2 sides, that is equal to the square of the hypotenuse. That's your Pythagorean theorem. Now, questions about that? All right. So let me do an example with this one. Let's verify the Pythagorean theorem for this triangle. So this measures 3, this measures 4, and this measures 5. Well, what we're going to do, let's label these. So let's say, we can say A is 4. Well, no, we'll call B 4. Call A is 3. And how we label A and B doesn't really matter. This could have been B, this could have been A. It's not going to make a difference. But this one, the side across from that 90-degree angle, this has to be C. It has to be C. So according to the Pythagorean theorem, a squared plus b squared, well, it should equal c squared. But does it for this triangle? Well, we know a is 3, so does 3 squared plus 4 squared equal 5 squared? Now, if we square these, this is 3 times 3, that's 9. This is 4 times 4, that's 16. Does this equal 25, which is 5 times 5? It does. So sure enough, the Pythagorean theorem for this right triangle, and it's only going to work for right triangles. It's only guaranteed to work for right triangles. It works. So that's the Pythagorean theorem. Now, sometimes we've got to do a little extra work. They're going to give us some problems where we got to look for things. So here's where that algebra comes in. Let's say I have a triangle. We need to solve for x. Well, how can we do it? Well, we can always use the Pythagorean theorem. So let's label this thing. The most important side to label is the hypotenuse. That's the side across from the 90-degree angle. So that's always going to be C. And then A, we could call this A. We could call this one B. That's not so important. So now what we're going to do is this. A squared plus B squared equals C squared. For a right triangle, that's always going to be true. Now let's substitute. A is x. It's unknown. B is 6. And C is 10. So let's compute these. We can't do anything with x squared because we don't know what x is. So we're just going to leave it. Now 6 squared, that's 6 times 6, that's 36. And 10 squared, that's 10 times 10, or 100. So now we're going to solve for x. We're going to use PEMDAS. Now, usually with PEMDAS, we would square and then we would add because we do exponents before we do addition. But in algebra, we're going to do the opposite. We're going to cancel addition and then cancel the exponent. And the way we cancel exponents are with square roots. So we cancel the addition first. Or here, let me write it below. And so what that's going to give us is x squared is equal 64. So here's a really important thing. When we're doing algebra, we're canceling. So we cancel squaring with square roots. We cancel squaring with square roots. And again, what we do to one side, we have to do to the other. So that means we can take the square root of x squared, and that means the square root and the square, they're going to cancel. But what we do to one side, we have to do to the other. So that leaves us with the x, and then square root of 64 is 8. And that's going to be our answer. Questions about that? All right. So there's some shortcuts with this where you don't have to use the Pythagorean theorem all the time. I just want to mention what these are. But these are triangles that have the same sort of ratios of sides. And you'll run into these from time to time. And there's more than the ones we're going to look at. But a famous one is the 45, 45, 90 triangle. And it has a base measurements of one side is 1, one side is 1, and the hypotenuse is square root 2. So let me do an example with this one. We can solve for x. So our angles of 45 degrees. Now, because, let's put this off to the side, because this is a 45, 45, 90, these two sides have to be equal. And so we find x is equal to 10. Questions about that? Another shortcut is this one. It's the 30, 60, 90. And its base is going to look like this. So let's say we have something like this. So you have 10, 20 at x. And this is 60. This is 30. And that's going to be 90. Now, another way you can think of this, and this was going to kind of help, you could think of this as 1 times square root 3, and this is 1 times 2. So whatever this is, this side will be whatever this is times square root 3, and this side will be whatever this is times 2. So what this means what we have is we can relabel this as 1 times 10. Oh, I'm sorry, back up here. This is going to be 10. This is 10 times 2. And this is going to be x. And for 30, 60, 90, x, and let me write this. Must be this side times square root of 3. We have 1 square root 3. We're going to have 10 square root 3. Questions about that? And again, these are just shortcuts. If you're not sure, you can always solve for x using the Pythagorean theorem because this is a right triangle. If this is getting confusing, you can use the Pythagorean theorem to solve for x. There's one more. It's the 3, 4, 5. And again, it has to have that 90-degree angle. It's the 3, 4, 5 triangle. And the way we do this, let's factor these. So this triangle well, we can rewrite this triangle. 3 times 7. 28 is 4 times 7. Then we have x. We have a 3. We have a 4. So what this does, and since x is on the hypotenuse side, x is 5 times 7, or 35. Questions about that? All right. So the last thing I'm going to mention, and we're going to do a little bit of 10.2 tonight. We might go a few minutes over. So we're going to get to ratios. So looking at section 10.2, we're going to be calculating ratios. And you might have heard of these. You might have heard of what's called SOHCAHTOA. We're going to get into this. Now, first off, when we talk about these ratios, take a look at a triangle. And what we're going to do, we're going to choose an angle. Let's say we're interested in this angle. And oftentimes you'll see angles written with a symbol. Sometimes it's this Greek letter theta. You'll see that there instead. But we could use A, that's fine. And this just says that we're interested in the measure of this angle. Now again, the side across from the 90 degrees, this is always going to be the hypotenuse. That's a special side, and it's always going to be that. Now, for the next two sides, it depends what angle we choose. The side opposite the angle we're interested in, that's called the opposite. And then the side that's next to the angle, but not the hypotenuse, that's the adjacent. Now, depending on how we choose the angle, things can change. Now, again, the hypotenuse, it's always across from the 90-degree angle. That's never going to change. But if we choose the angle up here, this is opposite, and then this side becomes the adjacent. So opposite and adjacent can switch depending on where this angle is going to be located. So now we can talk about the ratios. And when we talk about the ratios, hopefully this makes a little more sense, this SOHCAHTOA thing. Any questions? All right. So let's talk about these. The first ratio is called sine. The sine of angle A, and it's pronounced sine, like this. So the sine of an angle, it's the opposite divided by the hypotenuse. The cos of angle A, or what we call the cosine, Well, this is the adjacent over hypotenuse. And finally, there's the tan. Now, there are others. We'll look at these three. What's called the tangent. And this is the opposite over the adjacent. So these are the three main ratios for some angle A. Those are your three main ratios. And so one way you can remember these is the mnemonics. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. TOA, tangent is opposite over adjacent. And that's where that little mnemonic comes from. SOHCAHTOA. So let's do an example working with these. So any questions so far? All right. So let's say we have a triangle like this. There's our angle. This side, 148. This is 134. And this is 200. So what we want to do, let's recognize what these sides are. Now again, the side opposite the 90-degree angle, that's the hypotenuse. That's always going to be true. Now the side that's across from this angle, that's going to be the opposite. I'm going to abbreviate these. Then the side next to the angle that's not the hypotenuse, that's the adjacent. So let's figure out some things here. Let's look for the sine of 42 degrees. Well, the sine is the opposite over hypotenuse. Or in this case, 134 over 200. And that comes out, I'll bring in my calculator, about 0.67 here. Well, it actually comes out exactly to 0.67. So that's how we find the sine of that angle. Then what about the cosine? Well, cosine is adjacent over hypotenuse. Or in this case, 148 divided by 200 or 0.74. Finally, for the tangent, well, this is opposite over adjacent, or 134 divided by 148. Now this one I am going to round. It comes out approximately 0.91. Questions about that? So that's really the main thing for 10.2. I'm just going to touch on a couple things here. There's a couple types of problems you're going to run into where they're going to ask you to look for, they're going to use a calculator. There are two types of calculator problems. And one is finding the sine, cosine, and tangent using a calculator. So the first thing to keep in mind, you need to be in degree mode if you're working with degrees. So for us, we're going to be in degree mode. So that's a key thing on your calculator. You want to make sure that's what's going on. Let's see if I can find it on mine. Ooh. Let's see, is it setup? So if I go to setup, if I hit 3, that gives me degree. The alternative is radians. I want to be in degrees. I'm going to hit 3. And so this means my trig functions or my trig ratios, it's going to take the numbers as degrees. And I'll show you what I mean. So let's say we want to find the sine of 27 degrees. Now, the thing is in your calculator, on mine, and yours is going to probably be different. I'm going to hit my sine button. So I hit this button, then I type in 27. And then I hit equals. And so what I get is approximately 0.454. And that's it. Now, the key thing here, the reason this degree mode matters, when I type this in, I go sine 27, but I don't hit any special number that says degree. And this is just a common thing with calculators. You would think you would hit some special button to say, hey, this is degrees and not radians, but there isn't. Now check this out. Let's switch the mode. Go to setup, oddly enough, setup. My radians is number 4. So now I'm in radians. So now in radians, if I go sine, and then I type 27, and this, I'm not pressing plus here. This is just the sine button, then you press the 2 and the 7, and then you press the equals. Let's see what that looks like. Sine 27 equals, oh, I get a different answer. I'm going to circle this because we want to be working in degrees. The point is, if you're in degree mode, and if you're in radians mode, you're going to get two different answers. So for those kinds of questions, you want to make sure you're going to be in degree mode. Unless you do a problem, and I don't see any that you're going to get, but if it's in radians, then make sure you're in radians. So the last thing to mention, and thank you for hanging in there. I apologize for going over. Just want to make sure we're going to have plenty of time on Thursday to finish the topics. Finding an angle. So let's say you have something like this. The tangent of A equals 1.165 or 1 and 165 thousandths. Find A. Now, how do we do that? Well, what we have to do is we have to use inverse functions. Each trig ratio has an inverse function. So what this means, if there's a tangent of A, there's a tan inverse. And that's what this means. Now, what does it actually do? Well, I'll tell you in just a second. There's a sign. There's a sign with this funny -1. This means inverse. And if there's a cosine, there's a cosine inverse. So those little minus signs mean inverse. So how do we use these? How are these going to help us find this angle? Well, what we want to do is inverses cancel the ratio. The inverses cancel the ratios. So this is like cancellation we did in algebra. Now they have to match up, like only cosine and cosine inverse cancel. But this is how we solve this question. If you have the tangent of A equal to 1.165, then what we're going to do is take the tangent inverse of both sides. And what we do to one side, always the case in algebra, we do to the other. So we have an inverse and we have a ratio. They're going to cancel. The A is going to stay behind. So A is tangent inverse of 1.165. What the heck does that mean? Well, what it means is this. Inverse functions are on a calculator. So if we look at my calculator, I've got a tangent, and this is going to be kind of hard to see. But if you look at my tangent key, you'll see in yellow just above it, I don't know if you can see that very well, a tan inverse. So on my calculator, what I have to do is I hit Shift plus the tangent key. And this is going to give me tan inverse. And then I type in my 1.165, and then now I get my answer. So Shift tangent 1.165 equals, and that's approximately, oh, but I gotta be careful. I'm in radians. They're looking for degrees. Oops. Let me go back and go to setup, hit 3 for degree. I still want to make sure I'm in degree mode. Now, Shift tangent 1.165 equals. Get my equals here. And that comes up to approximately 49.358 degrees. And that's how you get that answer. Now, if you have problem finding your tan inverse, let me know. Another thing I want to show you, just mention this, Google, if you don't have a scientific calculator, you can type in trig ratio functions using Google. If you don't have a scientific calculator, Google actually has one. Let me take a look here. Let me show you real quick. And let's see, let me share my screen here. There it is.